Also, for instance, the losses, the inner losses of the antenna are described by the noise behavior and so on. And this is characterized with the help of the antenna measurement techniques. You will see that such measurement setups or measurement scenarios are not so easy to install or to realize. Yeah, and I also mentioned it not only one time. We have also to discuss about one signal which is everywhere on our Earth present. This is the noise coming from a temperature larger than 0 degree Kelvin. And this noise, thermal noise, we cannot cancel. The thermal noise, what we have on the surface, on the Earth, in rooms and whatever, depends on the temperature of the room and also maybe depends on the temperature of a device on which the antenna is mounted. That means it can be higher than the environmental temperature. And so also this higher temperature influences the noise behavior of an antenna, but not only. The thermal noise is a very important influence factor. Also, what comes after our antenna, namely preamplifiers, filters with their insertion loss, and so on. Then we have a chain of building blocks which influences, we say, for instance, the sensitivity or the noise behavior of a complete receiver chain from the antenna over preamplifiers, filters, and so on until the, let's say, final detector, or let's say the audio amplifier. You have such a system every day in your hand with your mobile phone, consisting of the antenna not visible, then not visible the preamplifier, then the filters, and so on. This is the receiving chain, and then you have the transmit chain, consisting of, let's say, a high stable oscillator, amplifier, modulator stage, down filters, final power amplifier stage, let's say designed for 1 watt, and then it goes again to the same antenna over special power combining systems, and the signal is transmit in the free space, and at least the same behavior or the same mechanism we have in case of an aircraft or an aerial vehicle, not only focused on aircraft. We will see it in the next slide. We have a lot of different aerial vehicles. Yeah. Okay, here we can see some examples of aircraft from Tupolev passenger and heavy, for instance, military Tupolev aircraft. I think a lot of them you will know. And if you have a look to the single aircraft, you cannot see at the first in the first moment where is the antenna, or where are the antennas for the different radio services. For instance, weather radar, it's necessary, and a lot of other things. And I will show you later that a lot of these antennas are not only nice to have. In the international air traffic, it's a must. It's must to have. And this we will see later on. Then in case of, for instance, military demands or military things, Then you have a lot of other antenna systems, especially based on radar systems that are on board of, for instance, such a large aircraft, which can carry several tons of electronic equipment. Or here we can see a passenger aircraft, which also has enough, let's say, percentage on carrier volume for the necessary electronic. Here you can see this white points here on the top of the fuselage. These are some antennas, but most of the antennas you cannot see directly. Here we have Soviet and Russian fighter aircrafts from Mikoyan, Gurevich, and Sukhoi. Such type of fighters also has, let's say, other things to do. Has another spectrum of radio electronics, not long-range radar systems, but more special radar systems like the so-called look-down, shoot-down radar and such things. And also here you cannot see in the first look where the antennas for these purposes are located in the fuselage. Here we have a very new part or very new type of aerial vehicles, the so-called drones. Here I show only unmanned aerial vehicles for military actions, but such drones are also available for a lot of civilian applications, for measurements of surface of the Earth, for architects to measure the, let's say, the area where a large building complex should be established and so on, and also for measurements of streets and all things, and also for agriculture. They can measure, for instance, the moisture on the surface of the Earth and deliver such data for agriculture. This also could be an issue for a drone, not only for military purposes. But this I only want to mention. And this, let's say, this area of application it's increasing, it's extending, because all or a lot of such things you can realize also with satellites, but a satellite, it's to bring in the orbit, it's much more expensive than to use such a small unmanned aerial vehicle, let's say drone, for special applications. Yeah, then another class of such aerial vehicles are the helicopters. Also here we can see the military application from, in this case, from Mil and the American Apache. And this helicopters also has a lot of different applications, not only military, also for transportation. For instance, transport of very large parts for building industry, bridges, parts of bridges, and so on and so on. There are a lot of typical, let's say, civilian applications, and also these applications have the need to have special radio systems on board, to fulfill these demands. And it's clear that it's different, or we have a large difference between the military application and the civilian application. This is a look at the history when, for instance, the radar system on board of aeroplanes or aircrafts are established. You can see here the first radar systems or radar antennas arrangement on the nose of German night hunting aircraft during the Second World War, especially fighting against the American and English bomber fleets. And you can see here, this is a very simple group of 4 directional antennas. It looks like a Yagi antenna, but it's not a Yagi antenna. It's only a 2-element dipole antenna. Working about these 4 outer antennas, working about at 120 megahertz. It's now our ultra shortwave radio frequency, and in the inner group, it's working in the UHF regions, means about between 500 and 600 megahertz in this range. And here, these are 2 different photos. This is let's say a Dornier aircraft. This is I think it's a Messerschmitt 110, and here you can see a larger group of antennas. This is a 4 by 4 array. This one is visible here, but we have here 4 such antenna groups, and these groups all working at the same frequency, means between 500 and about 600 megahertz. And this was again the first application of radar system on board of aircraft. It's clear coming from military applications, and this should show of, let's say, of a very short distance the enemy aircraft. And a short distance means between 5 and let's say 5 and 10 or 15 kilometers. Then the enemy aircraft or the bomber was visible on a very small display as a short peak, and they could then try to bring it down to Earth. Here you can see, let's say, what I mentioned before, the so-called must-have on radio systems for receive and transmit purposes, which are necessary on board of every passenger aircraft. It's not necessary in this moment to explain all these radio services in detail. It's only to show you which or what is the base. All these systems, the base means the base how to design a lot or a large variety of antenna systems, because all these radio systems necessary for a very different frequency ranges. If we start, for instance, with the nose here we have a weather radar. The weather radar, it's about located at 9 gigahertz range, about, and this is a completely other frequency range than what, for instance, the navigation systems has. For instance, here we have the global navigation satellite system. Here you can see the arrows shows the location of the antennas, and you know it's working about, for instance, GPS. It's the American system. GPS works for the military purpose, 1.2 gigahertz about, but for civilian application it's about 1.575 gigahertz. And Then we also have in Russian the GLONASS. I worked in this field of GLONASS and GLONASS in parallel, and the Russian system was more or less the single channels on in at different frequencies, and you have one let's say center frequency, and the single channels are decoded by bytes. And then we have, for instance, here the so-called glide slope. Then it's much lower than the weather radar. Then you can see also other systems, for instance, a marker beacon or the traffic alert and collision avoidance system. Of the aircraft in the near of the airport, and it works about at 1030 and 1030 megahertz and 1090 megahertz. These are the two frequencies may transmit and receive purposes. And I some years ago for production control for such transmit system, but not based on the aircraft. It was based on the Earth. It was a transmitter, also a receiver, but it works in the power range of 1 kilowatt. This is what I want to say. But also on board of such a passenger aircraft, we can have, we realize transmit powers in the range of several hundred watts, also up to kilowatts. For instance, the weather radar with peak powers several kilowatts. And so we can see, and this was meant in my outline, that we have at the antenna design, what the antenna has to withstand of not only of environment temperature, also, or in other words, which currents or which voltages the antenna has to withstand. So this is especially valid for the microcell antennas, because these antennas are use very small substrates and has very small distances between. And so, for instance, small distance by a given voltage leads to a very high electrical field strength. This can cause to, let's say, in principle, a lightning, yes, and this is not allowed. Okay, this is only for overview, so that you can see which different radio systems are located around the fuselage of this passenger aircraft, and what we have to consider in designing a special antenna which serves for one of these radio systems. Yeah, now let's come to the question, what is an antenna? What is the purpose, or what is the purpose of an antenna? And the first sentence, what you can find here, is most fundamentally, it converts the guided waves, for instance, present in waveguide or transmission line, into a radiating wave traveling into free space, or vice versa. So we have some keywords which we have to in detail to explain. It's clear the main keyword, it's the antenna, but then we have free space. What is meant with free space? What is a traveling wave? And what is transmission, and so on. Okay, then let's start here with the left side. You can see here the so-called generator or transmitter. In the simplest case, if we, let's say, speak only about a generator, we can say, okay, let's use only a sinusoidal signal source, maybe 1 megahertz or 10 megahertz, or doesn't matter in this moment. We only have a sinusoidal signal which can deliver at the output here, at the output of the generator, means at the input of this transmission line, for instance, of 1 volt. 1 volt is not so much, but only for as an example. It delivers 1 volt. Then with this 1 volt, let's say, as a peak value, and you know, in sinusoidal signals, you can say then the power equivalent value, the average is 1 divided by the square root of 2. It's about 0.707 volts. This is the equivalent value for power calculation. Okay, but let's assume again, 1 volt peak voltage, and then we have no information in this moment what is the power goes in the transmission line. So we have to know which is the, let's say, the input resistance or the input impedance, and not only general input impedance. Impedance consists of a real part and imaginary part. We are also interested in the real part. We want to know about some things about the power. Means we have to know the real part of this line impedance. And now you can see here, this line impedance, let be the value open until, then this is transformed step by step, or in this case, the steps are not visible. It's transformed with a smooth transition to the so-called wave impedance. This is the free space wave radiating in 3 dimensions, and the load of this free space is given here. This is the so-called wave impedance. This it's well known. Later on, I will give you some explanations how this value comes from. It's 120 pi ohm. It's a real part, or is a real value or a real part. Means this transition region of our antenna acts like a transformer or transducer, which transforms the given transmission line impedance, I speak about the real part, to this value 120 pi ohm. Okay, and if we assume we have 1 volt peak here, and we have, for instance, a transmission line impedance of 50 ohm, and the transformer or this tapered transition works correctly, then we have transformed this very high value, this 120 p ohm. We have transformed it then down to this plane here, output of the generator or input of our input line to 50 ohm. And in this moment, we can calculate the radiated power based on the assumption that we have here between this plane again means output of the generator or input of the transmission line. We have no losses. In practice, we can say if this is a more or less good conductor, for instance, copper, the losses on this in this area, if it's not very long, it's let's say short enough, several meters only, very low frequency, 1 megahertz, let's say 10 megahertz, it's low frequency, then we can neglect these losses. The losses in this case are so small so that it has no influence. And so we can say, okay, the output power which goes in the free space, it's 1 divided by square root of 2. And this is the voltage. And this we have to, for instance, divide by 50 ohm. And then we have the current is flowing in this line here. Yeah, and then we have to multiply it again by the voltage. So, and you can make a short formula on your paper, and then you can very simply calculate the power. This is the average value in square and divided by the 50 ohm. And this power, it's not very large, but we can, for instance, at this given low frequency, let's say several megahertz, then we can transmit this small power over a certain distance to a second antenna, and this is here visible on the right side, and the antenna on this location here is absolutely the same shape. It's the same design like here on the left side. But the only difference is here we have a generator, only sinusoidal generator, and here we have a receiver instead of this generator. And the receiver, it's only here visible as a square box with a symbol of an amplifier inside, but it's not all. Again, you need a preamplifier, for instance, or if it's necessary, a filter, and then let's say a power detector at the end. And okay, let's assume we have built in this receiver, amplifier, and at the end a power detector, and then we have let's say a measurement system at the end, voltmeter or a power meter. Then this points out or reads out the received power at this location of this second antenna. So in this moment we have absolutely no knowledge how large the received power could be, because we don't know how large is, let's say, the loss between this plane here, where the electromagnetic wave goes out, goes in the free space, travels through the free space, and it's now converted back from an electromagnetic wave in the free space over the antenna, over the same antenna like here. The same mechanism works now and makes of the electromagnetic wave an input voltage or input current or input power. The same what is done here in this direction, it's made in the reverse manner in this direction. Means here we create a transmit power, and here we receive a power, let's say received power. And between these two antennas we only have the so-called free space, means, at least if we look very precise to the behavior of the arrangement, we have to localize both antennas in not on the surface on our Earth, where the environment, it's air, it's a mixture of gases. We have to go in space, in free space. Then we have, in principle, the more or less theoretical background of this arrangement here. If we go to Earth, then we have not let's say the perfect free space. Then we have here a gas. This influences a little bit the behavior of this transmission path, but it's only a little bit. But nevertheless, in practice, if we fly, for instance, with an aeroplane in a let's say in a height of 1 kilometer or in the height of 5 kilometers parallel to the surface of the Earth, then it's clear then we can cross clouds, we can cross let's say an area where rain falls and so on. That means all these things between the two antennas, raindrops, fog, and so on, and such things influence the transmission. It's clear. Then it cannot be perfect like in free space, like between satellite to satellite. This is what I want to mention again. Okay, then for us, it must be clear one thing. This distance here, where we are working with the electromagnetic wave in free space, this distance has, let's say, no material losses. And so we could guess or assume that we have no losses, but we have losses. Why? Because we have to take into account that the electromagnetic wave, it's going out from here. It's making a phase front on the surface of a sphere, and so means the wave it's traveling like a bubble, and with a larger being diameter or radius, this surface comes more and more near of a plane, and but in a distance of infinity, then it's in principle a plane wave. But in a lot of applications, we cannot realize such large distances. Then in every case, we have very defined distances, and then it's clear that the larger the distance is from the transmit antenna to the receive antenna, the lower is the possibility to receive of the complete power goes out in the free space, to receive a part of this transmitted power to get it at the input of the receiving antenna. And this is the base on the, we will discuss it also on the so-called Friis formula. Again, we have here a generator, not modulate, only sinusoidal, delivers us, for instance, 1 volt peak in square. Then we have a half volt, we have the half power, and then we can here see that the wave goes out in the free space in a very large distance. At the input of the receiver, it's not an exactly plane wave, but it looks like a plane wave. It's clear that the radius here it's very, very large, and so we can assume that it's more or less a plane wave at the input, and then the antenna feeds the electromagnetic wave back to an input voltage at the input of the receiver unit, and so we can see at the output a certain power. But this power will be much smaller than the power which occurs here at the output of the antenna. Okay. This is how the antenna works, and to find a more or less deep understanding of the purpose of such an antenna. And now some words about the radiation mechanism. The second headline here, the necessary conditions for radiation, for radiation, it's shown here, or I try to explain it here. It's very simple. Let's assume a straight wire here, let's say a perfect conductor, or let's assume also a copper wire with a certain diameter, not too small, and I mean the diameter. And then you can see if you have only directed a current flow from the left to the right side, for instance, we speak about not a sinusoidal, we speak about DC current. Then we have absolutely no radiation. And what must happen, or what must happen that we can get, let's say, a radiation, not a sinusoidal radiation, what I have explained in the slide before. I mean, only that an electromagnetic wave goes out or goes away from this wire. Again, we have here a constant current flow. The current doesn't change the value over the time, it's constant. And now let's go to this example. We have the same current flow, but I break the current flow suddenly, let's say here in this plane, until to the time, from the time t0 to a time t1, the current flow is constant, no radiation, nothing happens. And then from t1 to t2, we break the current flow. And in this moment, we have radiation. And the outgoing radiation in this very short moment, it's determined by the time value, how long the breaks exist, and also the let's say the magnitude of the radiation is determined by the value of the flowing current, for instance 1 ampere. And what happens in this moment, if I break the current flow, then I have a time change in the current. And if I have a time change in the current, I also have a time change in the magnetic field around this wire. And I have also a time change in, let's say, in the power, which is not visible here, but there must be, let's say, a load resistance in every case. And also these values are determining the, in this moment, radiated electromagnetic wave magnitude or power of electromagnetic wave. The frequency, it's in this moment not exactly determined. It's normally it's a spectrum, like in lightning effects, or a spark, but nevertheless, we can, with a very sensitive sensor, we can measure that. For instance, with a spectrometer, we can measure that in this moment we have a radiation effect. Okay, another example, but it has the same background. We have a wire here. We assume also again here a wire, straight wire, with constant current flow. this is the position we start with our example, and then in a very short time we bend this wire, let's say around 90 degrees. And then in this moment, if we bend the wire in a very short time, for instance, we also can see, we can measure, let's say with a sensitive instrument like a spectrum analyzer, only in this time interval we can measure a small radiation. And also the basis that not only we have a time change in the current flow in this case, we have a change in the direction of the current flow. And this is has more or less the same effect. And now we came to the, let's say, normal case. We have here a current flow, but you can see this here in D, with a periodic change of the magnitude of the current. And for instance, coming from a sinusoidal signal source. And if the wire is open and long enough, in this moment, the wire acts as an, let's say, more or less as a antenna, and it radiates in around this wire body. Then we have also radiation. So for radiation, what is fundamental? The first thing is that we have a change over the time of the magnitude of the current, or of a change in the electromagnetic field. In all these examples, except the example D, we apply a DC current, and if the DC current is flowing without change of the magnitude over the time, no radiation occurs. If we have a time change, maybe by a break or the opposite of a break, we have no current, and then we have, for instance, here we have a gap between these wires, and then we connect the gap, mean we switch on a current circuit, then the current starts from 0 to a certain value, to 1 ampere, for instance. Also in this moment, then we have a radiation, not only because of a break, only because of an on, current switch on. In this moment, we have also radiation because we have a time change of the magnitude of the value of the electromagnetic field coming from the current flow over the time. This is important. And also here in this example, we have a time change of the current flow, in this case coming from a change of direction. Without changing the direction, the current flow is constant. And if I change the direction, let's say 90 degrees or another angle, then in this short moment, when I change the direction, then we can also see a very small part, it's radiated in this moment. And this is the, let's say, the standard problem. We have continuous change in the magnitude over the time of the electromagnetic field based on the current flow. Then we have also radiation from a single wire fed here with, or here it's a voltage source, and here, let's say, is the load, and then the voltage source is time varying, and so we have here radiation. Okay, this should be clear if we speak about conditions of radiation. And now we can go some further steps to understand how we can make from a, let's say, a general radiation effect more or less an antenna, or let's say an antenna which gives us not only a wideband spread signal, it should give us more or less a determined sinusoidal signal, means we want to transmit a message at a certain a certain frequency, not at a wideband spread or a wide spectrum. We want to transmit it at a certain point or a certain frequency in the spectrum. Okay, let's assume again 10 megahertz, for instance. Yeah, what we can do, here you can see a very simple arrangement. It's a inductance, a coil, and here we have, let's say, two fat wires or small plates or whatever, very close together. And this arrangement should carry, before I connected this to the coil or to the inductance, it's charged. It's charged with a certain value of charge. You know the formula. The charge, it's the product of the capacitance and the voltage. Q is C multiplied by U. And this value should have also the value, let's say 1. And in this moment, I connect the coil to this charged capacitor. Then it's clear, in this moment, we have an oscillation. It's not visible here because I only want to mention this because in this moment I connect the inductance. Then we have here a certain capacitance, a certain inductance, and it's clear then we have a resonance circuit. And the oscillation which occurs, it's only in this moment I connect the coil or the inductance to this charged capacitor. We have no external source, we have no external sinusoidal generator, nothing. Only this is charged by applying the voltage from a DC source, and then we can connect it. It's not possible to charge the capacitor when the inductor is connected. It's impossible because then we have here a short, in the case of DC, a short current. Again, you have to break it here. You have first to charge the capacitor. The capacitor is charged. And in case of, let's say, a dielectric material of air, the capacitor has a very, very high quality factor. The lowest quality factor is given by the inductance, as you know, because the conductivity of this material, for instance, copper, it's not infinite, it's finite, and this creates the losses, and so the quality factor of this parallel resonance circuit, it's limited. Means in this moment I connect this, then we have oscillation, a very short oscillation, goes down to 0 in a very, very small time. Let's say in a few microseconds, the oscillation ends. But this is not our problem. Our problem is the following. Let's start with connecting. In the moment we connecting the inductance to the charged capacitor, in this moment we spread the two plates of the capacitance in this way, and then it's clear this also changes the capacitance. The capacitance will be smaller, then the voltage it's increasing, but this oscillates. And what happens in this moment? It oscillates, and if the inductance, let's say, has a very, very high quality factor, then the reason of going down of the oscillations, of going down or decreasing the magnitude, it's not the quality factor of the inductance or the coil. No, this is the outgoing radiation of an electromagnetic field, what is shown here. You can see for a very short time we make the two plates in one direction. It looks like a dipole, and this, it's, let's say, this is the practical effect. So we deliver the energy here coming from, let's say, a DC source. We have no oscillator, we have no generator which delivers a sinusoidal signal. This is now created, or not created, it's delivered in the free space as an electromagnetic wave. This is shown here as an example. It's clear that we cannot do it by ourselves in such a short time. Open the two plates of the capacitor in microseconds and so on. But this is only for simplification, to create a deep understanding of how I can make from a DC charged capacitor, let's say a resonant circuit, which also transmits its energy, its electromagnetic energy, into free space. This is, let's say, one of a possible example for understanding, not to make it in practice. Yeah, and here you can see what happens if we open the two the two plates of this capacitance in such a way that it is a two metallic parts in a straight line, and it acts as a dipole. You can see. You can explain this vice versa. The first explanation is we can assume we have a generator. This R should be the inner resistance of the generator. And what is not visible here, it's the generator itself. Okay, we know that at the output of the generator we have here a voltage, and this is the reason why a current is driven into this dipole parts. And so we can see that we can create an electromagnetic wave, a sinusoidal wave, in this direction of the E field. The E field has the same direction like the direction of the dipole. And you can see here the change of the voltage along the dipole, plus, minus, plus, minus. And if we change the, let's say, the reason and what happens after this reason, then we have, for instance, an incoming electromagnetic wave. The green sinusoidal incoming wavefront should show this. And this E field, it's also in direction with the dipole elements or with the dipole parts. And so the incoming electromagnetic wave depends on the magnitude, creates at least at this ohmic resistance a received power determined by magnitude of incoming electromagnetic field, means of the E field component, or this is equivalent of the H field component, not visible here. And this makes, or it's the base on the received power at this load resistance. And in case of transmitter, the radiation occurs because the velocity of the charges is changing in time here of the sinusoidal function. But this is again what I have told all the time. The main reason of radiation is changing of the electromagnetic parts or current or voltage over time. Otherwise, we have no radiation. Here we can see this from another perspective. You can see also here this arrangement of a dipole. Let's assume it's a dipole. Here the two pins connected to the generator. And now you can see a very good how the outgoing waves are going along, let's say, the surface of a sphere. Here in the near field, it looks a little bit other. If we have a certain distance of the dipole, then we can see it's like laying on the surface of a sphere. But this will be explained in later slides. If we look now to, let's say, the environment of the antenna itself, let's stay here with a very small dipole. A very small dipole is also mentioned, or in the literature you can find it as a Hertzian dipole, but we will discuss this later on. Close to the antenna, what I have shown in the last movie, then the field patterns change very rapidly with distance. And if we have a certain distance of the antenna itself, then the so-called reactive part of the fields are negligible. Means directly in the near of the antenna itself, then we have a very large or very huge part of reactive field. Reactive field means this field components, or let's say energy saver, or it's not radiated. In this moment, it's changed only in between electrical and magnetical parts, changed, for instance, with the frequency, but it's not radiated. It's not has no real part, you can say. This is the so-called reactive near field region. It's in the direct in the environment of our antenna body. This should be shown, or is shown here. And this means the radius for this reactive field part close to the antenna, it's shown here. The radius must be smaller than this value here. What does it mean? Lambda is the wavelength, means it's another expression for the frequency. Then the large D, it's in our case here, it's only the length of the dipole, but in practice we have, let's say, much more complicated arrangements of the antenna. Then you have to use this D for the, let's say, the largest dimension value of the antenna. If you have, for instance, a dish antenna mirror, then it's clear, then it's the diameter of this antenna. If you have, for instance, a Yagi antenna or another, let's say, complicated construction, then you can find 2 points of the antenna, metallic points, which has the largest distance between these 2 points. And this value you have to insert in this formula. This is the large D. And here it's in by 3. And then you can see the other values, the square root of this relation. And if you are inside this radius, then means you are close to the antenna. Again, not only a simple dipole, it's also in this case a much more complicated construction or design. But then you are in the near of this antenna, and means the field patterns not determine the behavior of the antenna in the far field. It's only for the reactive part, and around the antenna, let's say the field energy, it's in this moment saved. And if you go away from the antenna, then the field patterns are changing very rapidly with distance and include radiating energy and reactive energy. And if you go more far away, then you will see that the energy comes more and more, let's say, as a real part. That means it goes really out of the antenna and goes in the free space. And here again, reactance which only stores, doesn't dissipate energy. It's clear. But again, this is in the near of the body of the antenna, let's say construction or antenna design or the antenna body. Then out of this reactive near field regions, we have let's say an intermediate zone between this radius 1 and between radius 1 and the radius 2. This is the borderline to the so-called Fraunhofer region. It's the far field. Then this is the so-called Fresnel region. This is not what happens in this region. It's not exactly this one, or it's not identical with the far field region. If you go out of this region here, means the Fraunhofer region or far field region, not the Fresnel region. Then we have to fulfill this condition. Means the radius of observation, what happens around the antenna or what the antenna radiates, the radius or the distance should be much larger than this value here. This is also the large D. This is the maximum dimension or the maximum points of the antenna body which you can determine of the metallic parts, and in square divided by the wavelengths. It's another measure from the frequency. And this quotient here, if this is much larger than this value, then you are with a high sureness in the so-called Fraunhofer region. And in this region, this is, let's say, our standard case. We want to measure and we want to see what happens with our antenna, what happens with the transmission of our signals. And again, the antenna, it's, let's say, this is the part of our complete radio system, which ensures that our signal comes from our transmitter into free space and also comes from the free space again back to my receiver chain or to my receiver output, or first of all to the receiver input. Without the antenna, it's not possible to make a radio transmission from point A to point B. And here in this slide, it's in principle another sketch, or this is another sketch, or it's a better visibility what happens in these regions. Again, we have here, for instance, this dish or this mirror here. It's, let's say, a satellite antenna. In the near field region, we have, let's say, such a field distribution. This is, let's say, the intensity or the magnitude of the E field over the diameter or over the opening distance of this mirror, of this antenna here. Let's assume this function. Then if we go in the Fresnel region, it's not far field, it's this between region. Then you can see this shape, but this shape is different to what happens in the near field region. And if we can assure that we are in the far field or in the Fraunhofer region, then you can see this is our pattern of the antenna which we want to have. Fraunhofer region. This it's here shown in Cartesian coordinates and not in a polar manner. Okay, so you can see that a measurement of the behavior of such an antenna, it's not. It makes no sense to carry out in the near of the antenna. You have to go very, very far away. And again, you can see here, this is the parameter D, what we have to use in the formula. This is the large D. These are the outer points of this mirror here, of this dish. And then if the wavelengths regarding to this D, it's very small. In case of satellite reception, we have wavelengths in the area of about 30 millimeters, 3 centimeters. It's 10 gigahertz, and normally it's higher. We have 11 or 12 gigahertz. But for calculation, it's a better value, 30 millimeters. And if the antenna has a diameter, let's say, of 90 centimeters or 900 millimeters, then you can see that the quotient is 30. 900 divided by 30, it's 30, and means if we switch back, if we look to the value, what is necessary regarding a suitable measurement distance, much larger than this quotient, 30. We can square it because we have only calculated the quotient here. Then we have to multiply it again by the dimension of this value of D, 900 millimeters multiplied by 30 multiplied by 2. Yeah, then you can see it's let's say 0.9 meter multiplied by 2. It's 1.8 meter multiplied by 0.3. Yeah, then you must have realize a distance of several meters, but again, or not again, or this distance, what ensures the Fraunhofer region, is also valid for instance, your receiving antenna. In practice, we have in every case 2 antennas. We have here the transmit antenna, for instance, and on the other side, we have the receive antenna. And this condition here regarding the fields around the antenna and far away from the antenna, these conditions are valid in parallel for both sides. You have to ensure this on the transmit antenna, this condition. The same condition you have to ensure it on the receive side. Means when we calculate here, this relation should be, let's say, several hundred, and then this condition, it's valid for the transmit side, but in the same time, this condition, if we also use, for instance, a large antenna, the same condition is valid for the receive side. If we have different antennas, let's say on the transmit side, a huge antenna, and on the receive side, a small antenna, then we also have to apply for each antenna these conditions. And then we can say, okay, then for measurement purposes, we can bring both antennas more close together. We will discuss these things, let's say, in connection with our measurement setups for determine the antenna patterns, and this, or in this case, or in these examples, what I can show you, or what I will show you, we will see, or we will find a more deeper understanding of what happens in case of measurement of the antenna. So let's say the aim of my first lecture was not to go very deep in mathematical formulations, but nevertheless, it should be clear that if we want to design an antenna, we must have some, let's say, some tools, some mathematical tools to determine the fundamental parameters of an antenna. For instance, given by the wavelengths, we have to transmit or we have to receive, or in other words, the frequency, the power, the sensitivity, what we have to achieve, or in other words, which distance we have to bridge from tower A or point A to a point B. These things you cannot only make with a sketch and with a sum rule. Then you have at least to use some formulas given by a very, very huge mathematical background from field theory, from Maxwell's equations as a fundamental base of all these things. And I only can show you or can give you some, let's say, snapshots or small segments of this mathematical apparatus or formulas, so that you can see what happens, or which, or let's say the critical parameters for antenna designs. So in current applications or development offices and so on, we do not use, let's say, the basic formulas to design antennas. Now we have high developed software tools, for instance, the so-called HFSS from Ansoft, or other tools, let's say, more developed in direction of planar antenna systems, or in brackets, microstrip antennas. There are a lot of tools, and I hope at the end of this lecture I can give you some hints regarding such antenna development tools. Maybe one of you has interest in designing antennas, maybe you have no interest, but nevertheless I will give you such hints regarding the software or suitable software. I will give it in your hand and you can apply it or not. Now, if we try to explain what happens a little bit in more detail regarding the direction of the electromagnetic field, means the E field components or the H field components and so on, then in every case we have to go in the field equations. We have to ask the Maxwell equations what happens with the electromagnetic field around a wire or around a small dipole. And these things I want to discuss with you based on this slide here. You can see here some formulas regarding the far field radiation from wires. This is, let's say, the title of this slide. And the antenna in this case is a so-called Hertzian dipole, means the frequency, the applied frequency from the generator or the wavelengths, it's regarding the dimension of the dipole, it's the wavelength is much larger than the length of this dipole. And now we have to look of two different parts. One part is the driven current in the dipole here. The dipole parts are red, as you can see here, and this small red wires are, let's say, the input connector. And here, where current at the coordinate 0, it's applied. Here we have also, this is valid, the coordinate value, it's for a z-axis, it's valid for the x-axis, and it's valid for the y-axis. Means this 0 has 3 different coordinates, and all are 0 means the dipole is placed exactly at the origin of this coordinate system. And yeah, the two parts are, it's the time variation of the current. In this case, we can assume it's sinusoidal. Another waveform makes the calculation much more complicated. That is the base of our discussion. All waveforms sinusoidal. Doesn't matter if sinus or cosine. It's only a question of the phase angle. And in this case, we have other parameters what we have to consider, namely what I have mentioned. It's the placement here in the origin, and also the change of the current along, for instance, the z-axis, or along one of these distances of these, let's say, localization parameters. The time is given by our signal source, the time variation, sinusoidal, given by the frequency or wavelengths, doesn't matter. And in the case, if the applied wavelengths is much larger than the dimension of this dipole, in brackets, Hertzian dipole, then we can assume that the current value, if we make a snapshot, the current value is changing with time, let's say with 10 megahertz. But we make a snapshot at a very short time in picoseconds or whatever. Then we can see that, let's say, the current goes not through 0. Let's assume he has another value, but along the dipole, this value is constant. This is the main point what I have to give you on the way. That means over the length of the dipole, the current distribution can be assumed constant. Has nothing to do with changing the current over the time. Again, the current over the time is changing after the sinusoidal function, but if we look along the dipole to every moment, and we can imagine we make a snapshot, and we can see a certain value of the current, then the distribution of the current, of this current value along the dipole, it's in principle constant, because the dipole is very short regarding the wavelengths. And under these assumptions or conditions, then we can, based on the Maxwell's equations, then we can find out the following values for the electromagnetic field strength here in different components. As you can see here, we have here in principle a Cartesian system, but this is let's say a half Cartesian systems, because we describe this with angles. The angle in this XY plane here, it's given by phi, means our dipole is localized perpendicular to this plane, or it's localized in direction of the z axis, and the z axis is also perpendicular to this xy plane. And again, around in this plane, the angle given by the relation between x and y, it's phi, and the other angle given by the z-axis and this xy plane, it's named theta. This is the angle theta. These two angles in connection with the distance to this field point, it's given here with the distance small r, and these two angles in connection with the r can determine a point over this origin. And we can, based on the Maxwell formulas, we can determine the field components at this point in a certain distance r from the dipole and under a certain angle regarding the xy plane, or an angle regarding, for instance, the x-axis to the y-axis. So we look to the single components, and we can see here we have a component E theta, and it starts with the J. This is an imaginary part, and this we will not discuss now. We only look to what happens with the r, with the distance. We have here in the denominator 4 pi r, then in the brackets 1, it's clear, then the r it's kept, and then if we multiply it here, then we can see we have here r in square, and here the r in cubic format. What does it mean? It means if we assume that we're very, very far away from the origin of our dipole, then this part here, it's super small in relation to this part with r is in square, and more or less we can keep only this value 1 divided by 4 pi r. Then we have the so-called r component, the theta component. That means this component is in direction of the radius, and here we have it, the r in square already, and here we have it in cubic format, and so you can say both components in a very large distance are we can neglect it. And in every case, you know that the H field and the E field, both field components in free space where we have no distortions, must be perpendicular to each other. So means we have a theta component of the E field. We also must have another component of the H field, and this is visible here. And at least we can see, if we look to the, let's say, the main components of this field components radiated from our small dipole, from the Hertzian dipole, we can see that we have in the r direction, the H field can be assumed to be 0. The theta component, this is the component connected with this E field, it's also, or can also assume to be 0. Then this component, E phi, it's also assumed to be 0. And so at least, wait, this field components are for us the most important things. And this is, let's say, the summary of all calculations, discussions, and so on. What is or what was done in the last, let's say, more than 100 years to investigate what happens regarding the far field or the field components of such a small dipole. In, for instance, in this coordinate system, if the dipole is located in the origin. And again, what it's important for us to keep in mind. First of all, I spoke about the so-called wave impedance. It's the impedance of the free space. Yeah, and the wave impedance, how it can be determined. This is shown here. You can see it's the square root of this quotient. This is the permeability of the free space, and this is the permittivity of the free space. You can look in some physical tables or with physical constants, and you can find these values. And if you insert this value and this value here in the formula, this is the funny thing, you will find out that the result is exactly 120 pi ohm after using the square root function. This is what happens. And this is very, very interesting that this comes out of a result. And the other thing, this is small c. I guess you know that it's the speed of light. And now you can see here, we have here this two, let's say, natural constants, this the permeability and the permittivity of free space. These two constants means that the free space is not empty. In a lot of, let's say, not very deep organized physical textbooks or half physical textbooks, it's written and it's assumed the free space it's completely empty. No, it's not empty, and this is visible here again, and especially here you can see that the speed of light also is determined by these two special constants, and so we come to the result that the speed of light cannot be infinity. It's given by this constant. It's 300,000 kilometers per second. And this is explained here with these two parameters. And I think this is a good connection for us, for radio engineers, to understand more or less based on this formulas why we have an impedance in free space, means a special relation between a electrical field strength and a magnetical let's say magnetical field strength. Why or how is the relation between these two two values? And you will see that and already you can see it here, that in case of the electrical part, the electrical field strength, you have here the wave impedance as a parameter in front of the formulas. And in case of the each field component, it's missing. It's not existent. Means both parameters are coupled also over this wave impedance, and this determines the magnitude relation between the electrical field strength or the electrical field components and the magnetic or H field component. This determines the relation between these two field components, the wave impedance shown here. Okay, speed of light, it's another thing, but yeah, makes the radio transmission, let's say, to very, very far away points, may say, let's say, out of the Earth in direction of free space, makes it a problem for, let's say, satellite communication and so on. What we can see here, it's only, let's say, a small mathematical play with this single components I have shown, or sorry, given here in this three formulas, and you can see here this it's named a radian distance, or it's 1 divided by 2 pi, and here the radius is given by it's normalized or given by wavelengths, and you can see here at this point of the magnitude of 1 of this part of the formula, and we have the other part of the second formula. If this is crossing the value of the magnitude 1, value of the formula again, then this is, let's say, the borderline here between this gray underlaid rectangular and here the white rectangular, means we have here in the gray area, the energy it's more or less imaginary. It's, let's say, it's in the direct environment of the antenna, and here we are in the Fresnel region and going out to the Fraunhofer region. That means from this point we are more far away from the near field behavior of the antenna. And if we look to the, let's say, to the magnitude values, means if you to be sure that we are far away from the antenna, then this value should be much larger than 1, and you can see this here, and means if we are here in this area and larger, then we are in the already in the Fraunhofer region or in the far field region, and in this region, only in this region, it makes sense to measure the parameters of the antenna, or let's say the patterns of our antenna. Okay, this is more or less explained now. And again, if we if we measure or if we look to our antenna in a distance much larger than our wavelengths, then we can apply this simple formulas, and we can see we have only in principle 2 field components which are perpendicular to each other. Yeah, now we come in principle to a next chapter, which is in the outline given by radiation pattern and directivity. Radiation pattern and directivity are, let's say, fundamental parameters of an antenna, and we have in every case to know these parameters so that we can look to what the antenna is doing. Is the antenna suitable for our purposes, or what we have to do to make the antenna better for our purposes? What does it mean? If we have to bridge a certain distance, let's say from a tower A to a tower B, or from a point A to a point B, then we can bridge this in such a way that we have 2 possibilities. We have a transmitter at point A, we have a receiver at point B. The distance, let's say, it's a it's assumed with, okay, let's say this small r, radius r. And we know that the energy of the electromagnetic field, because the electromagnetic wave travels with the function after a sphere. That means the wave goes out after with the sphere function. Then we know that at a certain distance, the power density must be decreased. It cannot be held to a certain value. It must be decreased, and so means at the aperture of the input area of the receiving antenna, by a decreasing power density, we have much small energy. The larger the distance, or this small r, the smaller the received energy. And again, we have two possibilities. Either we can realize at the receiving point or receiving localization or receiving point, we can realize the received energy of what we need on received power. We can realize this with antennas with a so-called very high gain, means very large antennas on both sides or only on one side. Or we can realize this if we increase on the transmit side the power. To increase the power, it's one possibility, but in this case we have to keep in mind to increase the power, for instance, instead of 1 watt, 10 watt or 100 watt. It's another thing in comparison to design a better antenna. The antenna, in our case, it's a complete passive device. It needs no external energy. The only thing what the antenna needs, it's, let's say, a good localization, or mounted on a tower and such things, and needs, let's say, more or less more material. If the antenna must be larger to realize the higher gain what we need, then the antenna normally has to be also much larger in the dimensions. Okay, and this should be my last sentence in this first lecture. As I know, we will see us not next week, or because there is you have event days next week, and so we on the 10th of May. Is this correct? It seems to be. I have no. Yeah, yes. Okay, now I can see you. Okay, so thank you so much for your attention. I close the lecture now, and we will proceed in the following manner. On 10th of May, you can, before we start with the second part of this, the second session of this lecture, you can ask me questions, what you have not understood, and so on and so on. And then I try to answer the questions if I know the answer immediately, or I have to think about and then give you the answer later. Okay? Thank you so much, and yeah, have a nice evening.
There was a question about the slides, if they can be handed over as well.
What type? They want to have the lecture completely, yes?
Mm-hmm. Maxwell asked it.
What?
Maxwell asked it.
Maxwell. then he should. I think it's if I give it to one person, then all other persons should also have. Okay. I will send it.
Yeah, if you would like to share, maybe you can prepare a PDF of it and
Yes,
send it
yes,
to
yes,
me,
I
and
have
I
it.
can spread it around.
I have it. I send it to you. I have the PDF lecture,
Mhm.
and I send it to you. Then you can go it around, give it around.
Yeah, good.
Okay, then see you 10th of May. Thank you so much for your attention, and bye-bye.
Mhm. Okay, bye-bye then. Have a nice evening, and
Same.
see you on May 10th.
Goodbye.
Later. Bye-bye. See you later.